Hello and welcome everybody. I would like to welcome Szymon Matkowski from Poland, from the Mars City org, and actually living in Moscow, as we learned. And he will talk about Mars colony base simulation of evacuation in Martian conditions. So you may start your lesson.
Okay, hello. Today I will talk on analysis of evacuation in Martian conditions with agent-based simulation software on the example of Twardovsky Mars colony biome. A few words about me. I'm an executive architect having 23 years of professional experience. I design big buildings like 60,000 square meters or greater, in which in fact can be called as small cities. Briefly saying I take the idea and make it happen. And one of the top priorities in my work is safety. Today, I will focus on one of the most important part of this issue, is evacuation. I will start with the principles of the design. So let's go back to the 1st century before Christ. Civil and military engineer, architect Marcus Vitruvius Pollio presented the histories, the architectura, where he defined a key triad of design directions, a triad which is to be followed by any architect, and now as space architect. It's a function, structure, and aesthetics. Globally speaking, while function is a reflection of people needs and activities, in other terms, mission goals, the aesthetics reflects all humanities, helps colonists mentally survive. The structure symbolizes all technicals to realize both previously mentioned. Me as an executive architect, I decided to focus on technical part of the building design. I've decided to establish a long-term goal connected to the technical part, to develop design standards, norm for base, colony, and even city design, where main accent is laid on people's safety. Safety of the people is a top technical priority in every building or device in any place. All architecture, structure, mechanical, electrical, plumbing, so-called MEP systems should be focused on minimizing the risk of life loss. So design of a base or colony or even a city or other planet or moon should comply with this principle. Therefore, my long-term goal is to define standards for designing architecture, structure, and MEP systems. This presentation shows results of current research on evacuation as a part of this main goal. Short-term research on evacuation of the people focus on a few directions. Occupants' movement speed in terms of reduced gravity, layout of major building elements for evacuation, passages, corridors, staircases, airlocks, safety zones, so-called refugee rooms. A simple example you may see shows the egress of the people. As you may see, early stage bases like 6-12 people does not require a significant analysis. But when things come to colonies and cities, such research is a must-be in a design process. Such analysis must be conducted on all stages of the design process, as details may influence the evacuation time. So, to conduct evacuation simulation, I use a specialized software, Pathfinder, provided by Thunderhead Engineering. This is an agent-based 3D simulation software. Agent is a virtual representation of each occupant. The result of such simulation is an animation showing fleeing agents. The key information for the designer is the time in which all agents completely escape the scene or are located in refugee areas. This is called successful evacuation. So, based on the result, time of successful evacuation, adjustments and corrections to building elements must be made. Like number of staircases, again, a correction of the width of the corridors, doors, or even an airlock capacity. After changes, the process must be rechecked and through numerous simulations, finally lead to the perfect design solution. As a result, strongly depends on various data. The software requires to conduct calculations on, we need to provide some additional data to the program, like agent profiles, which are physical characteristics of occupants, 3D scene, this is the building we want to test, and the scenario, which describes the main starting layout of occupants and their behavior during the evacuation. Now I will lead you through some of those points. First, I will start with agent profiles as they define a size and speed of each single occupant. These are the key parameters that software requires for each agent in order to conduct the simulation. While the size of an agent is identical to the Earth, people are the same. The movement speed changes significantly due to gravitational acceleration. Various scientific groups has conducted locomotion condition research in terms of micro and reduced gravity. But my study was based on result of a research published in 2014 by Francesca Silos-Labini, Francesco Laquantini, and Yuri Ivanenko. So to define the movement speed in terms of Martian gravity, the conversion formula must be used. The key of this calculation is the difference in gravitational acceleration. So to obtain the movement speed on Mars, we need to calculate the square root of Earth speed squared divided by the constant ratio of standard gravitational acceleration of free fall on Mars and Earth. Down below in the animation, you may see the comparison of the movement speeds of Mars and Earth for male 39-year-old. But the simulation to be closer to reality and reflect community diversity, multiple profiles must be used. Therefore, I created a table with converted values basing on Earth average walking and running speed, and the table is divided by gender and age ranges with their own recalculated data on speed movement. Also, an impaired mobility profile was created. As a reference for the simulation purposes, I will also use the Earth male 30-39 profile, which we will see in the further on in the animation, the red ones. So to suit all the software requirements, minimum, maximum, median speeds must be created, and the final data table is to be implemented into the software. The next element is a scene. The best 3D scene for the complex investigation is the one containing different type of elements, closed open spaces, zoned with high and low activity for tenants, all in one place. Therefore, Twardovsky colony base was chosen. It, as a reminder, is a second place winner on Mars Society Mars Colony Prize held in 2019. But for the software to work, original design requires some adaptation. Also, new areas have been added, like airlocks and safety zones. Briefly, Twardovsky base consists of 6 main living modules called biomes and technical production areas. Total number of people, including biome hotel, is 1,200 occupants. For the purpose of this research, I took one full biome. You may see it on the render view. So adaptation of it into the Pathfinder 3D model is a little bit simplified, but major areas were accurately reflected, like 5 main levels with living rooms and social amenities, food production area, common space on the main level, and in the bottom level, communication corridors leading towards other part of the colony. Now, scenarios are chosen to reflect non-standard situations where long reaction time or mass gathering might slow down the evacuation process. Scenario also reflect a starting layout for all occupants. Each scenario is tested on assumed evacuation time. For this research, I took 420 seconds, like 7 minutes, limit for successful evacuation as a basis. But to define a scenario, again, a few steps are needed. A definition of the population of the colony to reflect the variety of colony occupants. Occupants layout in the scene, which is a definition of particular starting location in the scene of each occupant. And at the end, the behavior of each occupant is to be defined, whether it's escaping to airlocks, safety zones, or it's even a panicking. For the scenario population, the colony reflects, the population reflects its diversification. It's important to involve all kinds of people into the simulation. This table shows assumed percentage population age ranges. I have simulated a sample layout, and as a basis, I took a female-male proportion as 50-50, and around 45% of the colony is relatively young to provide efficient workforce. Taking into the consideration also that colony is up and running for several years. So we have a better mix of age groups. The global percentage division can be converted into the real numbers as we, based on original Twardovsky design target, it's 1,200 people in a peak time. There is a slight change in population layout for the hotel part, as I assumed that guests would be rather a mid-range age groups. Let me underline that this is just assumption. And no doubt a start of the colony means presence of very fit people. They will be trained and capable of efficient movement during emergency situation. But this is not the case buildings should be ready for. It's better to introduce some less athletic groups to provide margins of inaccuracy of total simulated evacuation time. And further to base architectural, structural, and engineering solutions on such conclusions. Taking into consideration previously presented speed conversion table, population percentage layout, final chart of profiles work was created. Based on this data, it's now possible to finalize the scenario layout in the scene. Please pay attention to the colors because they will then reappear in the animation. The red one is the agent is the Earth reference agent. So two variants of occupant starting layer were selected based on the major rule that it should not reflect non-student situation. I called them late evening and weekend event scenario. Late evening assumes that tenants mostly are located in their rooms, resting after a Martian working day. Some of them are already sleeping. Therefore, reaction time since public announcement or alarm sound is longer than normal. Some people are located in common areas like canteen, sports room, but everything is calm and nobody suspects the alarm. Total number of occupants is biome bed capacity, which is original design 200 people, plus some late guests. The weekend event scenario assumes almost opposite. It is a day off. It's only 10% of colonies on duty to support normal base operation. But this time in biome, there is a community event held in a common space. Three-fourths of the colony is present. There are guests from other parts of the base. Some of the habitants are standing on the other levels in passages, observing the event. The rest is relaxing in the apartments. The total number of occupants is 855. Having all scenario assumption, what was left to do was to spread occupants in the scene. So based on population assumptions, particular number of tenants for each scenario, were distributed along the levels, basing on the function of the levels. 2 tables were created to show the number of occupant profiles, types, and spread into biome levels. Please note that there is a significant number of people on main common level in a weekend event case. So finally, the last part of the scenario is behavior of each occupant. Of course, the main goal of each agent is a successful evacuation. They will try to reach any exit or safety zone, but there are parameters that need to be defined to provide scenario realization. I have assumed first that panic behavior is excluded due to training and long-term being in the base. People who are relaxing and sleeping react in 60, 90 seconds after public announcement, but those who are awake and can understand better the situation are in common space, in open space, they react much quicker, that's 10 to 25 seconds. Finally, those who will not meet 300-second time of successful evacuation will flee into closest safety room. Please note that the time evacuation is 420. But knowing the timing for work of airlocks and possible crowd forming in the exit areas, it is already understood that these evacuees will egress time above 300 seconds, must run into safety zones to meet the overall time goal. So before I will come to animation and results, I will make a short resume on what we already learned. To conduct evacuation simulation, it's required to combine several initial data: agent profiles, scenario, and 3D scene. Agent profiles significantly depend on movement velocity. Profiles are to be divided by age groups representing diverse population, which for software means different speed ranges. Scenarios are chosen to reflect non-standard situation and must be constructed based on population in the colony, occupants layout in the scene, and behavior of each occupant. Okay, I will show you the result animation, and for sake of time, it's 4 times faster than normal, and there are some red agents, as already mentioned. There are at speed people to give you the reference. On the left, it's a late evening scenario, 200 people, 220. And on the right, the most intense scenario, 855 people during the day off. It's like community event. During the animation, please note the time reference given in the bottom right corner of each window. So simulation starts with a public announcement. In both scenarios, there are people in private rooms. On the left, there are almost all residents. On the right, only a few of them. They are relaxing, so the reaction for PA is longer. This in commentary area react much faster, and you may see crowds rushing towards exit on main level and residential passages. On the left, there is no big crowd forming. On the right, there are some residents seeing crowd jams already running towards safety zones. They quickly fill up and other must run towards staircases. On the left, you see safety rooms remain empty. Airlock provides almost smooth flow evacuees. On the right, you might see airlocks work on their full capacity, and slowly crowd jams are formed in front of airlock entrances. Occupants are awaiting next cycle of airlock to work. So people who have to wait for airlocks to work start to fill up main safety zones located nearby. They may be treated as compensation pockets. Safety rooms nearby airlocks require quite significant area to be provided. It might even become a common rule that safety pockets must be provided in places of biggest crowd gathering. On the left, even a long reaction time, and all the people flee in around 360 seconds. On the right, while safety rooms are almost full, people head again towards airlocks, and finally, all occupants are safe in 420 seconds. They managed to close last airlock door and evacuate. These animations show, in fact, highly advanced result of the research. I do not call it final. I have started with a few safety room and small airlock capacity. Throughout many simulations, it occurred that it was necessary to add up new zones and enlarge airlocks to get a present solution. So, resuming, safety is a top priority issue when designing a base, colony, or a city. Designing standards must be established to secure this issue. Evacuation is one of the key elements of those guidelines. Each iteration of crowd simulation leads to design update, changes resulting finally colony layout. With help of specialized software, which should be used on every design stage, it is possible to reduce the risk of life loss. Pedestrian movement and especially crowd forming in Martian conditions require further investigation, as most of the reduced gravity research focuses on single human being. And crowd behavior significantly may influence the design of further bases and colonies. And modularity of all major construction elements like staircases, lifts, corridors is a way to reduce the cost. But final forms must be investigated in many directions to provide open space and flexibility for further potential changes of the interior. And this is only the beginning of the research. Threats like decompression, dynamics of it, smoke forming, visibility protrusion, fire resistance of load-bearing materials and finishings all still needs to be investigated. All of this is driven only by one single purpose: to write down the norms with a pen, not with a human blood. Okay, this research would not be possible without the help of Francesca Silos-Labini, Twardovsky team, Thunderhead engineering team, and Mars Society Poland, which I really thank for support. Main animations are available on YouTube. I kindly ask our guardian angels to paste the links into chat. If you are interested in more elaborated description, you just can visit my blog, marscity.org. Thank you.
Excellent, thank you, Szymon. For our participants, the links to the animations that Szymon mentioned are posted in the chat. So if you want to take a look at those, there are YouTube links in the chat. And Perfect. We have some time now to take some questions for Szymon. If you have questions, just post those in the chat window and I'll pass them along to Szymon. Szymon, is there a standard for evacuation of a volume of an area that size? How does that work?
Is this a standard? I don't think it's a standard. Every single base you take, you need to remodel it and test it as long as it will fit the evacuation time. But as I already mentioned, the evacuation time depends on the smoke development, the compression time, the probability of hitting by the small rock. This part of this of the calculation, mostly I took the 420 seconds as a more or less international standard of the time you have on Earth to safely leave the building. Sometimes it's 5 minutes, on other countries it's 10 minutes, 7 minutes is something in between. So that's why 420 seconds. And the volume you calculate, it's the number of people you always have to drive from the functionality of the base. I don't know if I answered your question.
No, you answered it perfectly.
You always need to investigate how many people are inside.
Yes.
In fact, each base needs to have in every every functional area, it needs to have a counter for the people, which will then set up the evacuation systems. So they are ready for the number of the people. So they will be ready to take the people who will not be able to flee via airlocks or via corridors. They'll have to. There should be some pockets to protect people.
Sure, and it looks like as the population of the facility increases, the evacuation time would increase exponentially, not linearly. Is that accurate?
Yeah, that's true. But when you design the base in Martian conditions, you cannot just easily enlarge it. You need to design it for the maximum conditions. So even if the base in the beginning has like 100 people, you need to design them for 800. I know that is a cost, but in the future, then you will not have to demolish it and make it a new base. So people will live, will have this safety, protection and secure. They will be secured all the time. If you have 100, they will flee, and if you have 800, they will also flee. They will. But if it's going to be 1,000, it's part of it. Part of the people will need to have suits, or they will not flee. They will die. They will suffocate. They will die of smoke. And this is a kind of a risky. So you always design for the maximum of possible people in the area.
Thank you. One of our participants has a question. I'm going to unmute him so that he can ask that himself.
Hello there. I was just wondering if there was a disaster level event that meant we needed to evacuate, and that were to coincide with one of the extremely long Martian dust storms, is there also a contingency in that kind of scenario?
For the dust storm, if you are inside, you are mostly protected for all the external issues.
Yeah, but then say there was an issue inside the colony, inside the base, that meant you would need to evacuate. Is there a contingency if there was an evacuate from planet scenario at the same time as a dust storm?
No, I haven't seen that. But you know what? You can contact me via my blog, and I can evaluate that as well. No, I haven't done that. I haven't done that.
I will definitely reach out to you.
Yeah.
I would love to work with you on a potential solution for this.
Yeah, that would be cool, because whatever is inside, outside the building, the evacuation time. I've never done evacuation outside, for example. It's only inside. Outside, it's something completely different, but we can use the speed references and slow them down due to external suits, and slow them down and try to see how long they will have to have, how much time they will have to flee from the dust zone. But we can use a bouncing. I excluded bouncing from the evacuation time and from the evacuation, because I cannot imagine a crowd simulation with the bouncing people. They will just, it would be much harder even on the moon, because inside people bouncing mostly means injuries and protrusions. The most important thing in the simulation was a crowd forming in terms of reduced gravity. So the crowd is even longer, the crowd jam is even longer formed, and the people longer, take more time to flee to safety zones.
Szymon, just really
Reach
quick,
me out.
let me interrupt for just a second. For our participants, our next round of discussions is going to be beginning momentarily.
Yeah.
You're welcome to stick around and ask Szymon more questions if you'd like to for about another 10 minutes. But if you want to get to the next round of classes, those are just about to begin.
All right.
Karen, did you have a question for Szymon? I noticed that you were unmuted.
It's not.
Maybe not.
Maybe not.
I just wanted to say thank you for such a detailed answer today. And is there any chance one of the assistants could post a link to your blog? I did try searching for it, but there's several results that are all very similar.
You can see it just the big. You see the big Mark City arc on the presentation. This is what you.
Person had to spot that sooner, but no. Thank you.
Yeah, this is just so you just glow in.
Thank you for your time tonight.
Yeah, thank you guys.
I think I spelled that wrong. Let me try it again here.
Okay, I'll just write it down.
There you go. And do you have an email address that I can post, Szymon?
You want my email? All right.
Well, I was going to post it for them if you'd like me to, but that's up to you.
It's in my no, it's no problem. It's in my contact in my bio. So
okay.
This one. So I believe I sent it up to everybody.
Perfect.
Yeah. So if anybody can help me with this, with the estimation of decompression time or smoke evolvement time, it would be very helpful, because when I have a probability of hitting one by meteor a city, which is one millionth of per year per kilometer. With the size of a small rock, when you build a city which is like 20 kilometers square, it starts to be less than 1 millionth chance to be hit by the rock, and it starts to be a really dangerous a decompression time, and then evolvement and dynamics of it.
Szymon, you mentioned that as things get backed up trying to get into an evacuation airlock, there's an option for occupants to go into a safety room. Yeah. What is the protection that's available in those safety rooms?
The safety room, the detailed description is in my articles, also in the blog, but you have to have it hermetic, you have to have it provided with oxygen and food and water for at least 24 hours, maybe 48. You need to also have some kind of a door with a small airlock or small hatch that the emergency team can come with sleeve or with some kind of a device, a safety pocket that they can take you out from that and drive you into the safe part of the base. What I was thinking, it was a door with a small hatch that you took, you just connect the sleeve and you evacuate people via the sleeve. And people there are awaiting, like in bunker, they await for evacuation, for emergency team. If the people are trained, they are not afraid. If you need to survive somehow. If you're not managing the airlock, you need to protect yourself in some hermetic, protected from radiation and any other external influence rooms. They have to have, for example, separate engineering systems for the oxygen, for the water production, even a sewage, even the toilet. It should be a separate system from any other part of the base, and it cannot, of course, be as a storage or something that you will just put a lot of stuff, and then people will not manage to get inside because they will not fill it.
So
Yeah.
it's self-contained and self-sufficient.
Yeah, exactly. You need to have them. You need to have them and it's not only in one place. They should be spread all around the base. So because you never know which direction is to be the successful evacuation is to be held. You always need to have some small areas that some people just can run inside, close the door, seal it, and make a communication to the emergency team. I'm here. I need a rescue. This is also on Earth base buildings. You have such refugee rooms that they are protected like for 60 or 120 minutes of the fire, and you are perfectly sealed, and you just wait for fire guys, fire teams to be rescued. But of course, you have air, you have everything much easier. Even if there is a fire outside, it could be extinguished. And if you have a decompression, you cannot pump out the Mars environment, Mars atmosphere. You need to build it, and you need to evacuate people earlier. That was my point.
Sure, thank you. For your model, how much time does the airlock take to cycle?
The cycle for the airlock is like you have 5 seconds door opening, and then you have like 50 people inside. So you have this time to fill in, and then you have 5 seconds for the door to close, and about 20 to 30 seconds of pressurization. Of course, if you have inside and outside more or less the same conditions, the airlock works very quickly. But when the pressure drops down and people still not yet start to suffocate, it's like 650 hectopascals. It's like when you in a plane, when you have this breathing masks. This is level 4,500 square meters, and this is the level of the pressure you can more or less live. And as the pressure drops down in the base, which should be evacuated, there is a time for the airlock to work, and after that there is no need for the airlock to work, because people who are not in the safety pockets and they are not in the airlock, they're just dead. Because they suffocate. And or it's like that. So it's like 120, like 50 seconds for cycle for the airlock to work, but without the loading and unloading time. This is also, it's like more than 1.5 minutes for this.
Cool, thank you very much. Does anybody else in our audience have any questions for Szymon? I'm not seeing anything else come up.
I just wanted to quickly say thank you for your time today, Szymon. And I sent a message via the blog. I definitely hope that we can connect soon.
Yeah, you have my email or have my blog, whatever you like, and whatever time. Okay, thank you very much for this. Thank you, Lee. Thank you, Sabina, for this help. Thank you very much, guys.
Yeah, thank you, Szymon. Great job. All right, I'm going to go ahead and end the group
session,
here. Yeah. Yep, but thank you very much, Szymon. That was excellent. You did an outstanding job.
Yeah.
That was
Thank you.
very interesting.
Thank you, Lee. A very special thanks to Frank Crossman. He talked me to that.
Oh, yeah?
Yeah.
Well, I'm glad you were here. That was a great presentation.
Thank you. Thank you. Okay, so I stop sharing, yeah?
Yep, and I'm going to end the session.
All right. Thank you very much, guys.